Okay, now to help out a little bit, I wrote y prime minus ay equals 0. But of course, any solution here would be y prime minus ay equals 0, where 0 is the 0 vector. I've got an arrow over the 0. Okay, so because of the miracle that occurs with these dots here, we have this solution if the determinant of a minus lambda I equals 0, and from that it follows that we have our characteristic equation, and lambda has to be one of these two values. So our equation becomes 1 minus lambda 2, negative 1, 1 minus lambda times e to the lambda t times x1, x2 equals the 0 vector. Now the e to the lambda t is just some constant number for any value of t, so it can be factored out of the equation. And in fact, we can just divide through by e to the lambda t and get the equation that you see here, just the same as this equation without the e to the lambda t. And if lambda is an eigenvalue, then this equation has to hold, and we're going to be able to find an x1 and an x2 in the familiar way. It's just that we're going to get complex eigenvalues, so we have to do the complex arithmetic. So we choose lambda equals 1 plus square root of 2i. One less negative sign to worry about. We could have chosen 1 minus the square root of 2i equally well. And it turns out we're never going to have to look at 1 minus the square root of 2i, because the solution for 1 minus the square root of 2i comes out of the solution for 1 plus the square root of 2i. That comes out of the fact that these are complex conjugates and just the way the equations work out. And you'll see in a minute how that works. Okay, so if lambda is 1 plus the square root of 2i, then this equation, well, 1 minus lambda is just going to leave you this negative square root of 2i. So you're going to have negative square root of 2i on your diagonals, and your secondary diagonal, on your main diagonal you have those, and your secondary diagonal you're going to have the same numbers you did before. So now we have this equation. And of course the 0 vector is just the 0, 0 vector in this case, the compatible 0 column that has the same length as your x column. Okay, well, how do we solve that? We can write down the two equations. Multiply this row by this column, you get negative square root of 2i times x1 plus 2x2. Multiply through here, you get negative x1 minus the square root of 2i times x2, in each case equal to 0. Turns out that these equations are identical. If you multiply through this equation by the square root of 2i, you get this equation. You can check that out. Or you can just solve this equation, see what you get, then solve this equation, see that you get something that's totally compatible with what you get here. Or you can try to row reduce this thing. The second row is going to reduce to 0. Okay, well, what you get then from the first equation, I would rearrange that to 2x2 equals 2 square root of 2i times x1. Just, the negative here moves over to this side, becomes positive, and we get 2x2 to equal square root of 2x1i, so that x2, and things are getting a little fuzzy there in handling these boards. I apparently smudged this one, but let's make sure this is legible. I hope this is legible. This says x2 equals square root of 2 over 2i times x1. And that follows by very simple algebra from this equation. Well, that gives us any number of choices for our x1 and x2. The simplest choice is let x1 equal 1, then x2 is going to equal what? Square root of 2 over 2 times I. So our x1, x2 vector is 1 square root of 2 over 2i. Now we do that over here, so let me move this board pretty much out of the way, and I'll move it a little further out of the way as we get into this. Okay, so what? Lambda equals 1 plus the square root of 2i implies this equation that I've already written here, so that x2 is square root of 2 over 2i times x1, and we let x1 equal 1, we get x2 equals square root of 2 over 2 times I, so that our y is e to the lambda t times our x vector. Our x vector is our x1, x2, as we see here, and x1, x2 are 1 square root of 2 over 2I. So that our e to the lambda tx becomes what? Well, our x is 1 square root of 2 over 2I, and lambda is 1 plus the square root of 2I, so it's 1 plus the square root of 2I t, e to the quantity 1 plus the square root of 2I, quantity times t. Okay? So here's our y vector. That's a solution. Now, e to the a plus b is e to the a times e to the b. Just a property of exponents. So that e to the 1 plus the square root of 2I times t is e to the t times e to the square root of 2it. Very straightforward, and I think you're pretty much used to this. And that still times our 1 square root of 2 over 2I. Well, e to the square root of 2it is cosine square root of 2t plus I sine square root of 2t. We are used to the Euler formula, so that should be no surprise. So that our y is simplifying step by step. We come down to this, and then we can multiply through by e to the t times the cosine square root of 2t plus I sine square root of 2t. And we get this. Here we just get that expression. Here we get that expression multiplied by square root of 2 over 2 times I. Now I started to rewrite that here. Let's just smudge that out. I wanted to come up here so we could see it a little better. So again, what have we done? We've written we've made our assumption that y is e to the lambda t times x, and we've plugged that in to the fact that the determinant of a minus lambda I has to equal 0 in order for this equation to be solved. We've evaluated the determinant, giving us our characteristic equation, which we solved to find two values of lambda. And now we've gone through the process of plugging all that in and finding an x1 and an x2. And this gives us a y function of this form. Now, we simplify this. We expand e to the t cosine square root of 2t plus I times e to the t sine square root of 2t. We've just distributed the e to the t through here, broken this into real and imaginary parts, and we've done the same here, remembering that we've got an I here, which when multiplied by this I will give us a negative on the sine of the square root of 2t, and an I on the cosine square root of 2t. So the i's on the cosine, you have the e to the t, and for the second component you have the square root of 2 over 2, and you have the negative on your sine with all the rest of the stuff, and you can easily see how that all works. Okay, well now there's a great big payoff, and I have enough time on this video that I could talk about that, but I'm going to start another video. So at this point, okay, we've gone through the messy algebra and we've got this. So let's see where we go from there, and let's see what our payoff is.